particularly, we are interested in how these modes grow in space and time. So, a natural way to do this is to look at the growth of the modes in a frequency space. And by frequency space, I mean frequency both in time and in space. That is saying that u prime, which is a function of x and t, is going to be expressed as a summation. It's kind of a Fourier analysis, both in the time domain and in the spatial domain. So it is a summation, or so discretely it's a summation. If you do Fourier transform, it's integration either way. So summation or integration in the space of alphas and omegas, where alpha and omega are complex numbers, of u hat as a function of alpha and omega and y. So the reason y is not expanded in frequency space is because y is a non-homogeneous direction. Right? So y, as you traversing y, you are going from the wall to the free stream, and it is not a homogeneous direction. It doesn't make sense to expand the y direction in terms of waves. But in the x and time direction, it does, because time naturally is a homogeneous direction. As you increase in time, you don't expect the boundary layer to change. Also, when you go downstream in space, we know the boundary layer changes very slowly. If you assume that the wave number of these waves, of these growing or decaying and evolving waves, the wavelength is much smaller than the characteristic growth length scale of the boundary layer, or let's say the x location of the boundary layer. Then you can expand the x in waves. So the resulting expansion is, I times alpha times x minus omega times t. Right, so these are this exponential of I times something is basically cosines and sine waves. Right. So that alpha, let's say if alpha is purely a real number, that means it's basically a perfect wave in space. And if omega is a perfectly real number, then it is a perfect sinusoidal wave in time, right? But if alpha has an imaginary component, that means the wave is not just repeating itself in space, but also grows or decays as you increase in the x direction. Correspondingly, if you have omega that has an imaginary component, that means it's not a steady state wave that just oscillates periodically. It's a wave that oscillates and also grows in time or decay in time.
So at a single fixed x location, if omega is complex, it can.
That's right.
It can grow.
It can grow, yeah, or decay, right. So, what we are interested in this case is a boundary layer that is macroscopically speaking is steady state, right? If it has any amplification of small disturbance in time, it has already reached a certain steady state. So we are interested in the case where omega is perfectly real. And we are interested in looking at alphas that are not perfectly real. Okay, so we are interested in sweeping over all possible frequencies in time, that is, all kinds of oscillations in time, and find out, are these oscillations going to grow in space or decay in space? So are these oscillations waves that are become bigger and bigger as I go downstream, or waves that are becoming smaller as I go downstream? So if there is any wave that becomes bigger and bigger as I go downstream, these waves are going to be amplified. So if there is, for example, some sound wave that comes into the boundary layer and becomes these particular waves, okay, through some receptivity mechanism, then we are looking for these waves. So what are the waves that gets preferentially amplified? So with this expansion, it is therefore enough to look at. So okay, so also these equations are also linear equations with respect to u prime and v prime, right? So it is okay to use the principle of superposition and look at only one of these terms, look at each of these terms separately. So looking at each term separately for a fixed alpha and fixed omega, alpha and omega are constants, not a function of x and y or t, but this function is a function of x and t. So the x derivative and t derivative can be taken as derivative of the exponential, that is partial t becomes minus I omega times something, right? Partial x becomes I alpha times something. So this differential equation is going to be eliminated in the t and x directions, leaving only a differential equation in the y direction. Yes?
In this case, like alpha, would that, like, you were talking about something which decays, right?
Mm-hmm.
So would that be imaginary in that case? Value of alpha?
So if alpha decays, then it has to have a positive imaginary component. Okay.
Should it be negative? If it's decaying?
Oh, no,
If it's, I mean, because you have an I square, you have an I in front of that, you have I square, right? So if it's growing, alpha would have a negative imaginary component.
But it's complex in general.
It's complex in general, right? I mean, if it's perfectly real, then you have a certain kind of wave that neither decay nor grow.
It's only like oscillates.
Yeah, only oscillating in space. That's right. Okay, so by substituting this into the equation, what you get is minus I omega times u hat plus, so this is time derivative, this is spatial derivative, plus u prime. So I'll write the prime as the y derivative. V hat is equal to minus I alpha p hat plus Re inverse u double prime. So that's the y derivative and x derivative. Oops, what did I? Okay, x derivative. Okay, and the corresponding v equation is this, the same thing, but without this term. It's p in the y direction, so I have a prime plus Re inverse v hat double prime, also same thing here. All right, so these are the two equations I have. Yeah.
For the first equation, the third term,
Yeah.
you said that was v prime times partial big U by partial
V prime partial big Y. Yeah, so I wrote it yeah, that's not a good notation maybe. Because I used the prime. Okay, so the prime now is the y derivative. So let me actually write it down. So partial y. Okay, so I also have the prime here. So it's partial square y and partial square y. All right. I think that's all the y derivatives I have. In addition to that, I also have mass conservation. So previously, I didn't write down the mass conservation, but the mass conservation is partial u prime partial x plus partial v prime partial y is equal to 0, right? And the x derivative can be replaced by I alpha. So I have I alpha times u hat plus partial y of v hat is equal to 0. All right. That allows me to replace, basically that means my u hat is going to be I over alpha times partial y v hat. So basically I can get rid of all these u hats in these two equations. Okay, so by getting rid of all the u hats in these two equations, this becomes a single equation, a fourth order equation. So that's called the Orr Sommerfield equation. And that's only a function of v hat. So it's we have the alpha here minus omega here, and the second derivative of v hat minus alpha square v hat minus alpha times the second derivative of u hat times v hat, and plus imaginary number times Reynolds number inverse. There is a fourth order derivative of my v hat minus 2 alpha squared times the second order derivative of v hat plus alpha to the fourth power of v hat itself is equal to 0. So that's the equation that governs the decay or growth of unsteady modes. Okay, so this is basically simply by combining these two equations and this relationship. All right. Okay, so this is a fourth order equation, therefore requires how many boundary conditions? 4, right? And what boundary conditions do we have?
At the wall, v.
We know v hat at y equal to 0 has to be 0. How about v hat at y equal to infinity? That's also 0. That's the amount of disturbance I have, right? What else? Yes, u hat at these two locations also has to be 0, which means the y derivative of v, both at y equal to 0 and y equal to infinity, also has to be 0.